Okay, I'm on pointer number 3 now for the day. I like green. All right, so we're down to the last hour. I like questions. Ask them at any time. Getting some good questions. So I realized, I'm almost afraid to mention it, my computer has not shown an encryption message today. As soon as I mention it, it's going to, so I don't know. Some people have asked about imaging temperature, and this is a great picture. This is a picture from one of my students. By the way, he was a Princeton student, actually, a Princeton undergraduate, Mark Thurber. So what I want to do now is I want to talk about what you can do by combining PLIF with flow tracers, where you might be interested in a lower temperature flow below maybe 900 degrees Kelvin, where the tracer would still be chemically stable. And so we'll look at some flow tracers. The first one that really became important was acetone. That's a ketone molecule. I'll tell you about that. Slightly bigger version of that molecule is called 3-pentanone. That's now been used in IC engines, especially at Sandia, but also in probably in Wisconsin. We tried to look at CW PLIF rather than pulse PLIF, and I'm going to end up with some work on toluene, which has a lot of potential for doing temperature. But this was a picture almost 20 years ago of the flow over a heated rod. It was a soldering iron. So the soldering iron flow over the heated rod, temperature from around, this is called the repeating color code. So this is like looking at fringes. So you have to kind of look at this. It repeats between 420 and say 380. So it cycles every 40 degrees here between blue and blue. But this was pretty good. This was a single shot image of acetone seeded flow around a heated rod. And so if you do this with a fixed mole fraction, you're just looking at temperature. So that's a great picture. And I emphasize this one because I have some later in this talk, and I realized this morning that somehow the images have lost their color. I don't know how I did that. So this is the best example I have of what can be done. So a 10 nanosecond picture of the temperature around a heated rod. So this is a heat transfer problem. So if you're a heat transfer person, this gives you an idea of what you might be able to do. Now it's in an open environment. Everything gets harder if you have an enclosed environment. Why? Because you have all sorts of surfaces that scatter light. Remember, fluorescence is a weak process. It's in a lot of light. And you're going to collect a little bit. And one of the things you do is you try to collect light at a different color than the laser light. That way, the scattered light, which is mostly at the same color as the laser light, can be rejected. But remember, it's very strong, so you have to do and it gets harder when there's surfaces or when there's any particles around. Okay, so this was this historic picture of the first PLF image. It was a 100 by 100 photodiode array cropped down, so we don't have nowadays you can buy these things with megapixels. We had only 10,000 pixels. It's an interesting story, since I might have a little extra time. Kitchikoff was a really good student from Australia who now has a company in the state of Washington. Howe was my technician, who now is a professor, chaired professor at Harvard in biomechanics. He was a really bright guy that I was able to hire. He graduated in physics at some university in Oregon. McDaniel is a professor at Virginia. Okay, so we have potential energy wells of some kind, because we're usually doing this with electronics transitions, which have big oscillator strength. And we've seen this equation that relates our signal to basically how many photons go in, what fraction are absorbed, what fraction are emitted, what fraction are collected. It's kind of an easy way to think about it. You have to send in light, you have to absorb light, you have to have a useful quantum yield, and you've got to collect some fraction of the light that's acceptable. What we'd like to do is we'd like to control this fluorescence quantum yield. This is the killer. This one right here is the source of trouble. Remember, that's that A over Q term? That's the one, and the uncertainty of Q is which gets us. So how can we do to overcome that problem? So we're going to see this flow with some sort of a tracer. We're going to record some image on that camera, and this is a simple reflection of that. All right. Biacetyl and acetone were the first tracers used. So now, people have done fluorescence in liquids. And that may have actually preceded our work to do this in gases. I'm not sure. People were using fluorescein dye in water and using doing some fluorescence. But we had as an interest, we have to do this in the gas. And of course, liquid is 1,000 times as dense as the gas, so the signals are bigger in liquids. It's harder to do it in the gas. And so there's been a sequence as we moved away from, initially from biacetyl, and then we went to acetone. Those were the first ones used. So you'd like to do it in air, but you can't use either oxygen or nitrogen because they don't have accessible absorption spectra. They both absorb it down into the vacuum ultraviolet, which is not acceptable. So I had this student who became interested in doing some, he was a fluid mechanics student from Cornell. He was interested in looking at mixing, and we came across a compound called Biacetyl. I think we found an article and said that you could get fluorescence from this. But it's like a kind of a, it's a liquid which you could evaporate, but it was really smelly and hard to handle. It would really gum up the plumbing, and it's highly quenched by oxygen, meaning that biacetyl, when it contacted oxygen, had a very high Q, so that the fluorescence yield was small. Nonetheless, we got started with this, and this is the structure of this molecule. There's 2 methyls and 2 double-bonded oxygens here. That's the structure of this biacetyl. Looks like this. It worked well. Then one day, after about a year, we had a leak, and some of it went out the building, and the people next door complained, and they said they were going to get cancer, and so they shut us down. So I had a really good Spanish student named Antonio Lozano, and I said, find something else. So he did a survey, and he looked at a variety, maybe 10, 20, 30 different possible flow tracers, many of which are toxic, and so we were really worried about toxics, so we wouldn't touch those. But he came across acetone, which is kind of similar in structure. So here we are with acetone, this one single, it looks a bit about like this biacetyl. And he came across acetone, and we started to study it. And then a little bit later, the Europeans groups in, especially Germany, found something similar. And then we had a big conference as to why our results didn't agree. That was an interesting story. But the fact is that acetone has become really popular as a flow tracer. And it has a virtue that it doesn't, is not impacted by the presence of oxygen. So that was important. So oxygen, for some reason, is a highly effective quenching agent, and so it reduces the signal. So how can we use a PLIF of tracers? So here's our ketone molecule, and here's the absorption spectrum of that molecule. So this is more or less, it's somewhat temperature sensitive, but this is probably room temperature. It absorbs, has a peak absorption around 260 nanometers, which happens to correspond to an available wavelength you could get from a quadrupled YAG laser. So the YAG laser is just a box, emits light at 1.06, but you can do frequency quadrupling, and out comes light at to about 260. If you absorb light from a ketone or acetone, where's the fluorescence spectrum? What's the emission? Emission's over here. So important, you realize that the fluorescence emission occurs at longer wavelength, which means lower photon energy than the absorption. So you absorb here, and then what happens is that the molecules want to change states rapidly in this molecule, and they emit back down because of their Frank-Condon factors to different states. So you absorb here, fluoresce here, and now you can use a spectral filter which captures only to the right, and you can reject the scattered light from the laser. So that's a good idea. Advantages of these ketones are that they give strong signals. What does that mean? That means it has strong absorption, and it has a good quantum yield. Yeah?
Is that behavior because of Stokes shift?
Because of the Stokes shift. I wouldn't call it a Stokes shift. You could call it a Stokes shift, I suppose, because the emission is a longer wavelength. It's because, remember in the Frank-Condon thing, you have, the transitions are vertical from the ground state that you're absorbing to the excited state, but the emission can occur at different colors. And it's almost always because the laser wavelength overpopulates. So you go from, say, an average energy state to an above average energy state. It's not at average temperature. And so the emission occurs at a different color. It's almost universal in fluorescence that the emitting wavelengths are longer than the absorbing wavelengths. I guess you could call it a Stokes shift because the emission is at a longer wavelength, but it isn't due to a Raman effect. It's not a Raman process. It's absorption followed by emission. So it may still be called a Stokes shift. Stokes shift, but it's a fluorescence process. Okay, so the virtue of this is that it's accessible. It's at a wavelength that we can reach pretty easily by fairly economical, powerful lasers. We get this non-resonant fluorescence. It's resistant to bath gas effects, meaning it's not very sensitive to oxygen. It's fairly similar to hydrocarbon fuel, so if you want to use it in a combustion environment, it may kind of track the combustion species, the fuel. So you might be able to use this in some sort of fuel-air mixing. You could trace the fuel with this species and imagine that this species tracks where the fuel is going. So you form it into a sheet and take pictures with what now would be a CCD or mostly CCD cameras. So it's pretty, now if you have an isothermal and an isobaric flow, meaning the temperature is uniform, pressure is uniform, then the signal is nothing more than proportional to mixture fraction. So if you want to do a mixing experiment at constant temperature and pressure, all of a sudden the quantum yield is a constant. Now it's going to be easy to interpret. So that's really the power of this idea. So the ground state of acetone is called a singlet, so an S. So for these big molecules, you use an S for singlet and a T for triplet. And you use a 0 for the ground state and you use a 1 for the first excited. So there's the electronic state of the acetone. Here's the first excited state with the same electron spin. There's the so-called T3 state, which is nearly coincident in energy with the singlet state. So if you imagine that you're exciting an average molecule in this ground state, meaning it has this amount of thermal energy. You go up to here, that length of the arrow would be the length of the energy of the photon. What can happen? You can fluoresce, which is what you want, and the lifetime of that is 2 nanoseconds. Remember that lifetime is 1 over A. So that's telling you what the A value is. Or you can undergo transfer to this triplet state. You actually could stay, there's another process I'm not going to tell you about. You can go over to this triplet state, and once you're in the triplet state, triplets are forbidden to do this, which means that it happens, but it's weak. That's called phosphorescence. So if you hear the words fluorescence, that means it's allowed. If you hear the words phosphorescence, that means it's forbidden, but it happens with an average time that's much longer. In fact, so this phosphorescence lifetime is 200 microseconds. So if it's here, on average, it takes 200 microseconds before it emits. Whereas it's here, it emits in 2 nanoseconds. So clearly, if you're here, you have 2 choices. You can go this way, where in case you kind of die, or you do this. So the quantum yield is going to be the ratio of this rate to this rate. What is that rate? But anyway, back to acetone. It has a good vapor pressure at room temperature, about 180 torr. It's cheap, non-toxic, easy to handle, has a good fluorescence lifetime, and it's independent of oxygen. So you can do this in air or you can do it in nitrogen. Now, that means that if I take this number, the A coefficient here and the Q transfer rate here, it turns out that this Q transfer rate is independent of conditions. It's a constant. And so that means that the fluorescence quantum yield, which is really A over the sum of A plus Q, which is essentially A over Q because Q is much bigger, is a number. That's great. All of a sudden, the fluorescence quantum yield is a number, a constant. And all of a sudden, our fluorescence equation becomes very simple. So the fluorescence signal would be proportional to the number density of acetone times the intensity of the laser. So you double the laser intensity, you double the signal, this one. So this is the mole fraction times the total number density of the mixture. So if you're doing this in an isobaric, isothermal environment, This is going to be great. So Lozano discovered this along with a postdoc that came from Yale, at Brandon Lip. Yep. And back to this again. So this was the absorption spectrum for acetone. And I think I mentioned, he actually analyzed a lot of possibilities, but concluded acetone was the safe one. Looks like the peak is more like 275 nanometers. So, and then here's the fluorescence spectrum. Peaks out here at around 500 nanometers. Why do you care about that? You have to use a detector that responds to the wavelength of the light. So if the light is from about 400 up, you can use a visible camera. Whereas if the light is down at shorter wavelengths, you have to have a UV sensitive camera. So this is looking good. We actually chose to excite the acetone at 308. That was because we had a 308 nanometer laser that's called xenon chloride. So you could have a xenon chloride laser, you could have a quadruple YAG laser. I think at that time we might not have had the quadruple YAG. That would be at around 266. So you want a simple laser. The laser is just a box. It just sends out pulses of light. You form them into a sheet, and it becomes a relatively simple experiment. So I'm going to show you some really great results that were done by a student named Scott Smith. He was interested in the jet and crossflow. So here's our jet of acetone-seeded nitrogen, I think it was, or air, I can't remember now. Wouldn't make any difference. So we have the jet going into a crossflow. The jet velocity is 20 times the crossflow, 20 to 1. So here's a case where the jet velocity is 20 times that of the crossflow. And all we're seeing is a picture of the mixture fraction. Because it's isothermal, isobaric, it's proportional just to the mole fraction. So this is an amazing picture of the jet mixture fraction, an instantaneous picture for this jet. This jet was about a 5 millimeter jet, and the crossflow was 5 meters per second, so it was about 100 meters per second coming out here. This was an unintensified scientific grade camera, which we bought at that time. So it was not too expensive, but it did not have an intensifier, which made it better. And then, so you can look at, you can take images along any line that you want. If we take the distribution along this line from this picture, here's the instantaneous distribution. So what you'll see is that if you looked at some sort of a textbook, it would show you a distribution that looks smooth. But the instantaneous structure in reality is really quite complicated. These are all so-called trailing edge vortices. If you look along this line, you see this distribution. Again, so see the power of this technique to look at the instantaneous mixture fraction. I'm sure that, well, I suppose the fluid mechanics people might think they can calculate this now, but I don't think they can calculate it correctly yet. It's a pretty complicated flow. So, but the virtue is that because it's isothermal and isobaric, the quantum yield is a constant. So what you do is you fill the chamber with a certain amount of acetone, you illuminate it with your laser light, you collect the fluorescence image, and you have just measured the intensity distribution of the laser, which you need to interpret these signals. So you have everything you need. Now you can take a picture in this horizontal plane, that's looking down, that's what you see. Or you can look at it from the end, this is what you see. See this interesting structure here? Here's the bottom of the tunnel, and this is the distribution along that line. So this is the transverse plane, the plan view, the end view. Look at the structure that you can see with this idea. So this did get the interest of the fluid mechanics people. Of course, you have to pay attention to the Reynolds number and that sort of thing. So in order to do this sort of thing, you need to either, you want to pick a tracer which has the right properties, pick a laser, pick a camera, and if it's isothermal, isobaric, you're kind of done. But if you're going to do a flow field in which temperature and pressure vary, you need to understand what I'll call the photophysical parameters. So we got into this problem when we wanted to apply, to do flow tracing of a compressible flow field. Now, it's not constant pressure, it's not constant temperature. You need to understand how temperature and pressure come into play. So the equation looks about the same. The signal is the photons in, the path length, number density of the absorber, which might vary with position. Here's the photophysical parameters. the absorption cross-section, and the fluorescence yield, and the collection optics. So the signal is always proportional to the number density, but now modified by the absorption and the fluorescence parameters. We need to understand how they vary with temperature. In this case, the cross-section doesn't depend on pressure, it's just wavelength and temperature. And this depends upon wavelength, temperature, and pressure. And if it depends on oxygen, it also depends on oxygen mole fraction. So this model, so Mark Thurber built this model. It's still used now around the world. And it looks pretty complicated. It's not as bad as it looks. So down here, you have to imagine in the singlet state a whole bunch of energy levels. The average energy level would be that which corresponds to the room temperature or the temperature of your experiment. That photon comes in and takes the molecule up here. Now what happens? There's a family of processes. That's the problem. You can have fluorescence from any one of these levels, or you could undergo collisions and because of vibration relaxation, keep going down between collisions. Or you can undergo what's called inter-system crossing, or you can have oxygen quenching if that's important. So the trouble is, there's a family of processes that affect Q, and they may vary with energy in this manifold. So here's an example. We think that as the energy is going up, that this crossing rate, we express this as a rate coefficient, this is really Q, changes with energy. So that was a complication. We expect that oxygen quenching may also vary with energy. So the trouble is there's a family of processes. They may be energy dependent. How do we extract the behavior of the parameters up here as a function of T and P? So we build models, we do laboratory experiments, and we measure those parameters. This is an example of what we have to do. So we might measure the relative fluorescence signal per molecule for this 3-pentanone. So 3-pentanone is like acetone with one more carbon instead of hydrogens here. So there's 5 carbon atoms. So if we excite at 308, we see the signal, and here's temperature, we see that the signal per molecule is kind of constant and then dies off. If we excite at 266, which is a quadruple YAG, we see it dies off pretty fast. If we excite at 248, which is a krypton fluoride laser, so what do we see? We see that the fluorescence signal depends on wavelength and temperature. That's both good and bad. That means that if you want to measure temperature, there's some new tricks. So if I look at this result, and I come over here in nitrogen, although with these ketones we could have done this in air. If you come over here with acetone, what you'll say is, well, let's take the ratio of one of these temperature-dependent signals and the less temperature-dependent. So if I took the ratio of 308 to 266, that's this red line, I'd find that the relative signal per molecule changes from about 1 to 9 over 400 or 500 degrees. So what if I take this one? What if I take the ratio of 308 to 248? Look at this. This is amazing. The very, very, very strong temperature dependence. That's what you're looking for. Something that gives you good signals, and the relative signal is extremely temperature sensitive. So you use ratios of colors. Now, of course, I have to have 2 lasers. I have to have 2 lasers, and I have to record 2 images. But you understand the photophysics like this, and you can pick your experiment. Acetone, 308, 266, we wouldn't really do that. But look, even this simple pair right here, we get a factor of 10 gain over a factor of 3 in temperature. So that's pretty good odds. This is the picture that was supposed to have been in color, so somehow it went bad on me. So here's an experiment. We used 266, that would be a quadruple YAG laser. So these are lasers that have no knobs on them. They just pump out energy. You use some optics, you form it into sheets. You stagger one to be right after the other, maybe a microsecond, and you can record on a camera. Now, if you use a camera that's called a frame transfer camera, it can take 2 pictures in the same camera. So that way you have the same spatial resolution. You don't have to worry about synchronizing 2 cameras. So that's a powerful idea. So you use a frame transfer camera, 2 images, 2 microseconds, freeze the flow. Unfortunately, these didn't come out. They're supposed to be in color. So What's the power of this? You would take the ratio of the two images to get temperature, and that's this right here, which would have been a nice picture, but I lost the color somehow. The ratio gives you the temperature, and then with the knowledge of the temperature, you can get the number density or the mole fraction. This was an experiment at constant pressure, but variable temperature. So I can get I can do the mixture mole fraction. So that works really well. That's a good scheme. You could just use the same scheme in a compressible flow field also, because the temperature would be independent of this pressure. And you would get now, from this you would get the you get the partial pressure of the species rather than the mole fraction. But if you knew the pressure locally, you could convert that to a mole fraction. So that's a pretty good idea. Okay, so I'm going to now show what my students did with IC engines. So everything's harder in an IC engine. Why? Because you've got surfaces. If you want to image inside this engine, here's the region you want to image, and here's the inlet and exhaust manifolds and so on. They use what's called a bow ditch or bow ditch configuration. So you might send in a horizontal sheet of laser light and you look through a transparent piston, take the light out here. That's a conventional thing to do. So it's optically accessible through the piston. You also can do it with a transparent cylinder in another way. So you want to look inside, and this was done at Sandia. In this case, he was using 308, which is xenon chloride. He formed it into laser sheets of 50 millimeters by 0.7 millimeters thick, 45 millijoules of light, and 277. How did he get that? He had to do Raman shifting. So he took this light and you send it into a tube filled with hydrogen, and you get a Raman shift, and you can produce 277 nanometers. He wanted that pair. So this is tracer-based PLIF in an engine. He used this particular line pair. Let's see, this would have been Dave Rothamer, professor at Wisconsin now. Now there's two strategies. You can use temperature, you can get the temperature by looking at the ratio, and then from that you can do simultaneous T and mole fraction. Or you can use single line, but with homogeneous composition. So if you seed it, if you're just looking at the compression stroke and you had a fixed mixture flowing in, then you could use the single excitation to get the temperature. That's the single line concept. He used 3-pentanone. Good sensitivity, minimal effect of oxygen. What was he interested in? In HCCI engines, they're very interested in the thermal stratification because that temperature controls the ignition. And they did this both in motored, which means non-combusting, and fired operation. They were looking at the early mixing and the thermal stratification. So they wanted to measure very small changes in temperature and mixing. Here's some results. Pentanone, isooctane, vaporized. Let's see, we have, here's temperature. And there's temperature at different crank angles, basically. And here's the color code. So you'd look at this particular time, which is early, and see that there's some cold gas in the blue, as well as some hot gas in the red. And you can see how the mixing goes. And so by the time you get to 100 degrees, it's pretty well mixed. And the range in colors now is kind of right here in this range here. He's probably measuring to 15 degrees or so. Mole fraction. Now he's looking at the mixture, and he's inferring the mole fraction of air by seeding one stream and looking, we call this the negative method, and he's taking a difference from one. Anyway, this is the mixture of air, the mole fraction of air he can infer, and what we find again is by 100 degrees it's mixed. So this high mole fraction of air here corresponds to the low temperatures. He was especially interested in this EGR. It's called internal EGR. So this all has to do with mixing and temperature. So it's pretty powerful. How good is it? Well, you look and you see how well can you resolve temperature when it's mixed. And it looks like it's probably 10 degrees, 15 degrees. I'll hold it. This became Jordan Snyder, so he's at Pratt & Whitney. So we went from being interested in HCCR to being interested in EGR. Okay. Now, he was doing this, he did this in motored and in fired. I think you look over here, this is a temperature result. And look, by 340 degrees, he's still able to resolve really small temperature differences here, around 980 to 1,000 degrees. So this is really his most beautiful work. He was able to resolve local cold and hot spots of just maybe 5, 7 degrees. Now, it took a couple of years for him to get to this point. We had to understand the photophysics database first. He claims 4 to 5 degrees of precision, which is very important for ACCI. So in ACCI, the idea is that it will ignite where it's the hottest, and you would like it to either be completely homogeneous or you actually want it to be stratified so that the combustion wave will progress. So temperature is everything. Okay. He claimed that somebody asked me about heat transfer. He claimed that the heat transfer to wall surfaces was responsible for this cold spot, and that the irregular heat transfer of the surfaces would lead to pockets of cooler gas that would convect into the core and affect autoignition. So heat transfer affects the temperature, which affects the ignition that they're interested in. Okay, so what's the problem with that? If the laser is running at 10 hertz, you actually only get one image per cycle of the engine. So you'd really like to look at the time evolution. And so I worked for a while on this idea of using a CW laser. So what if we used a continuous wave laser in toluene, because it gives us really good signals, to try to look at continuous wave LIF, PLF. So now the idea is that we used a 5-watt diode laser, frequency doubled to get us to 266 through some cylindrical lenses, and by that point our power level was about 1/4 of a watt. Remember now, with pulse lasers you get 100 megawatts or some incredible number. But you can integrate over a longer time. So he looked at a jet, and this, by the way, this jet's going from top to bottom. It's a jet with 4% toluene, 7mm jet, fairly high Reynolds number, and we're looking on our camera, ICCD camera. So the question is, could you use a CW laser, so you're always illuminating the flow, and then use a high-speed camera to take pictures at any repetition rate you want, rather than being limited by the pulse rate of the laser? That was the idea. And we know what the problem is right away. We don't have enough laser power. That's the problem. But how far can you go? And we were interested in how far we might be able to go to look at turbulent mixing. So we wanted to look at a CW PLIF, toluene seeded, steady nitrogen jet, well, steady, but with fluctuations present. 266, cavity doubling of commercial 532, really cheap experiment. Intensified CCD, so we need an intensified camera. So the question is, how far can we go, and what sort of time resolution and repetition rate can we get? So this is a figure that I'll try to explain to you. What's the minimum detectable fluctuation in mole fraction? So you have a jet, and you're looking at fluctuations in mole fraction of this of the jet fluid. It depends on how big a region you look at. If you look at this is still a small region. If you look at a pixel that's 50 microns by 50 microns by 400 microns thick, and then as a function of the laser power, we could resolve out here at where we were, about 200 milliwatt, we could resolve about 3% fluctuations. Meaning if you're looking at a picture, if you could see differences of say 3%, they were real fluctuations. But if we're willing to go to 400 microns by 400 microns by 400 microns, and to do a little binning of these pixels, then we get way down here. So the point was, with an exposure time of 100 microseconds, so if you're willing to look for 100 microseconds, to integrate the signal over 100 microseconds, which is still a short time, and if you're willing to live with 0.4 millimeters by 0.4 millimeters by 0.4, we actually can detect 1% fluctuation. So that's still pretty good. So sometimes you design an experiment to be compatible with the capabilities that you've got. That's still a pretty small region. I mean, 0.4 millimeters by 0.4, that's a pretty small region. And we could do that at 10 kilohertz. So that's the framing rate for 100 microseconds. So we could take 10 kilohertz pictures with our CW laser with this sort of high spatial resolution on a camera. Here's some pictures. Remember, this is a downward flowing jet. And this is toluene seed Now, actually here he was only using 10 microsecond exposures, corresponding to 100 kilohertz framing rate. And our laser power had drifted down to about 200 milliwatts. And he's doing this for 50 microns by 50 microns. So this is really pretty high spatial resolution. If he averages a bunch of signals, he gets the mean. That's easy. If he looks at a single shot picture, he gets this. Here's the relative concentration. And if he takes the difference between any single shot and the mean, he can resolve these fluctuations pretty well. These are down to a few percent. So that is a pretty good experiment. It would be a better experiment if he would have been willing to stay a little longer before he left me. But anyway, it's a good experiment. If we could go back again and we get a more powerful laser, I think this is a pretty good idea. If you need to frame at higher speeds than is possible. Now, meanwhile, people have developed pulse burst lasers, so you could argue that the way to do this is buy one of these $500,000 lasers that give you pulse bursts. But this is a poor man's way to do this. Okay, what's the future? Here I think we want to use higher powers. We might want to use a beam homogenizer so that the beam is uniform in intensity. One problem with imaging is typically the beam has an intensity distribution and it's not uniform. And you'd like it to be uniform. So we would probably fix that problem. Okay, there's an interest in temperature, so we can go back to toluene again. And we're going to try to look at the same equation. And you want to control the photophysics so that you can image temperature. And I'm going to show you some results that we took in a shock tube. Where our goal was to image temperature, but recognizing that the temperature image also is dependent on pressure. So we built a special end section for the shock tube. The shock tube runs from left to right, and the end of the shock tube is right here. And somewhere back here, about 3 meters, we went from being round to square. So now this is a square cross-section shock tube. And we put windows on the end and on all sides, but on the opposite, okay, windows on 2 sides, slot on the top, window on the end. So it's almost a full optical access chamber. And we want to see what the temperature looks like in the velocity boundary layer. And we want to see how close to the surface can you image. That was the goal. So here's a result. And he tried doing this a different way. Here's the pulsed UV laser formed into a sheet. You could form the sheet and go through it horizontal, parallel to the floor. You can come through the vertical top and make it perpendicular to the floor. You can come in from the end at different orientations. And what he was looking for was what's the configuration that allows him to get closest to the surface. So here's a case where he had the horizontal beam. He was looking down. And so here's the end wall, and here's the diaphragm's down. The shock wave's coming this way. Here's the end wall. Here's the shock wave. And so what do the different colors mean? The different colors reflect the different fluorescent signals. And we know that the shock wave should be a straight line. And we know that the gas here, if this is an incident shock wave, this is the room temperature gas. This is the shock heated gas. It should be uniform, And we can look at the statistics of the signal in this region and say something about the performance of the system and its sensitivity to temperature. In this case, the post-shock temperature here was only 440 degrees. Shock speed is moving about 600 meters a second. And the student's name was John Yu. Well, that's what you do to see if everything's behaving properly. Do we understand how the signal varies with pressure and temperature? Because we know the pressure and temperature here, we know the pressure and temperature here, so we can make sure we understand the photophysics. So we were interested in how close you get to the surface, and also there's a problem with, there's a few shock tube people here. This is called the reflected shock bifurcation problem. Here's the end wall, and the incident shock has come down, reflected off, and gone back. What I've told you is the shock wave is planar, yes. When it goes back, however, it has to move into a sidewall boundary layer. And here's a distance of only 4 centimeters. So we're looking at a distance here of maybe 3/4 of a centimeter. So there's a boundary layer, which we're able to see. There's a shock wave which is now curved because it has to have this triple shock structure. And this should be a uniform region. You see the boundary now of this, this is called the jet here. So anyway, we're able to examine the structure of this fluid mechanics disturbance. Now, people have studied this before, but they used line of sight interferometry. I think it's the first time anybody used a spatially, temporally resolved structure technique like we are. And he could take these at different times. This is 100 microseconds after the reflection. So the reflected shock had gone back about 3 or 4 centimeters by that time. Now at 150 microseconds, what we see is this region starts growing. And we try to interpret these regions in terms of the interaction of the shock wave and the boundary layer. There's also some heat transfer going on at the end wall. Longer time, so now the shock wave has passed out of our field of view at 200 microseconds. Now, we have to repeat these experiments to do this because we only have single shot systems. So we do the experiment and image at 100, 150, 200. So what are we showing you? The ability to look at the structure of a strongly time-varying flow field. And we can interpret this in terms of, so it's uniformly seated. The mole fraction is the same everywhere. So the only thing we have to worry about is pressure and temperature. So unfortunately, different regions have different pressures. Pressure is one pressure here, another pressure here. And pressure is nearly constant in here, but there's some structure. So to convert this to temperature takes a little bit of work. And I believe we could apply this to a lot of interesting flow fields. I want to compare briefly the experiment with the simulation done by some colleagues in the ME department at Stanford. They had a code called Charles. All you can tell right now is that they look pretty similar. They can resolve some things that we can't because they don't have the noise problem that we have. But they're generally consistent. I like these pictures. So this is a case where you really blow this up and look at the structure here. You can see the angle of this shock wave, angle of this shock wave, the structure here. So if a change in color occurs, it's due to pressure and or temperature. So because the mole fraction is the same everywhere. So they're really looking at turbulent structures in the shock wave boundary layer interaction problem. These were just different times to blow this up. So what do you see? You see the potential for doing imaging that's nearly quantitative in time-dependent turbulent flows. He did some work to try to look at the convective motion of certain features. This one, and so on. So you could get some convective flow velocities from that. Okay. I want to end up with talking about temperature imaging using 2 cameras. So in general, we have to worry about the fact that the mole fraction is not uniform. And so we're interested in using 2 cameras. We're interested in using toluene because it's such a strong signal, although toluene usually we use with nitrogen. You could do this with toluene, which means basically no oxygen, or you can do it with a ketone, which means you can use air. And the idea is that you would take 2 images. This would be a flow over a supersonic flow over a wedge. Here's the flow from left to right over this wedge. So we know the temperature is in this zone. And we take the ratio of those images and get temperature, and we can compare it with a calculation. So in this flow, the temperature is uniform in this region, temperature is uniform in this region, and only varies slightly along that wall. So it's a calibration picture. Okay, how do we do this? We want to use 1 laser, and we want to get 2 images. How can you get 2 images? So you recognize that the fluorescence distribution is slightly temperature dependent. And when you increase the temperature, you increase the light that is emitted at longer wavelengths. That's 320, 340. So basically, if you blow this up and you look at, this is the fluorescence distribution as a function of temperature from 297 up to about 770 Kelvin. So as you go up in temperature, there's not much change over here. The change is always at the longer wavelengths. So that suggests that you should use filters and use 1 filter placed here and another filter that captures everything to the right. And the ratio of those signals is going to be strongly temperature dependent. And you can calibrate that in the laboratory if you wish. And then you can decide, well, did I buy the right filter? You can say, well, I can play with the characteristics of this filter, play with the characteristics of these candidate filters, try to decide which one's going to give me the temperature sensitivity that I need. We looked at 3 sets of filters. And you want to make sure that you have enough signal. So you do experiments to see how to optimize these filters. So now this would be a single laser, single camera with 2 filters, or single laser, 2 cameras, each one with its own filter. And then the question is, what's the ratio of those signals as a function of temperature? And here's the plot that was done ranging from reference value of 300 degrees. And this is what you get with these particular filters. So you can get a ratio of about almost 5 as you go from 300 degrees to 1,000. It's not nearly as sensitive as some of the stuff I showed you earlier, but it has the potential to do this with a single laser. So the student did this. This was Vic Miller. He did this with our expansion tube tunnel and the flow over the wedge. And here's his result for the temperature. There's the temperature here, the temperature here. Here's the temperature in this shocked gas, or the flowing gas, and then the shocked gas here. So is it perfect? No. You can see the noise level. Can we discriminate temperature change? Yes, 460 to about 6. So it works, but we might wish it were a little better. But it is a way to do compressible flow fields. He's looked also at cylinder flow. So this is flow over a cylinder front. And we can get really nice looking images. These are single shot, this is the CFD on the bottom, and this is the PLF on top. So they agree. The quality of the CFD is higher than the PLF signal, of course. And if you look and blow this up along the line, and you compare the stagnation streamline here, which is this one, you can kind of get comparisons with the theory. So you look at this as a way to help you improve your experiment. You look at this and you say, how can we do better? What are the things it would take to reduce the variation? And then you can go back to the jet and cross flow and start looking at these. So these were now pretty recent, within the last couple of years. Jet and cross flow images of temperature. So how do you do that? You have to seed the flow, and you take the ratio and the toluene, and you get pretty good looking pictures. It's really cold here. That's 200 degrees. Coming out, it heats up. Here's the bow shock. That's really the state of the art. Okay, so that brings me to my very last slide. So what I was trying to do is start off with the theory of spectroscopy, telling you about rotational, vibration rotation, electronic transitions in diatomic molecules. We illustrated this with some quantitative absorption. We moved into the infrared, especially because then you can use high tran and not have to know very much about the spectra. I think I told you that HiTran has just released a couple of software packages that make it easier and easier to use those databases. You have to be careful when you take those low temperature databases and use them at high temperatures, because there's some flaws in the spectra, because those spectra are sometimes calculated, sometimes measured, and they don't have much high temperature data. They're especially weak when it comes to line broadening. But it's a great tool. And you bypass the need to know a lot of the theory. We looked at some example applications such as shock tubes and different kinds of engines. I showed you air propulsion and energy conversion systems. And I ended up by telling you that I thought absorption had a lot of potential for applications in control. So absorption is cheaper, user-friendly, real-time, accesses many species, combustion products especially, but you always have to worry about whether the non-uniformity along the line of sight is a problem. PLIF. Then we went to imaging, planar laser fluorescence, which gives you ability to spatially resolve flow fields, complex flow fields, but the hard part is to make it quantitative. There are tricks to making it quantitative, both for reactive species and tracers. So what I'm hoping to do, and I tried to end on example applications to give you a sense as to where is the field, and hopefully end on positive examples that show you it's worth your time to know enough about the spectroscopy to use these techniques. So I think if you're interested in combustion, fluid mechanics, heat transfer. Hopefully what you've seen is that spectroscopic techniques have a lot of value for you. There's a lot of potential applications. I'm interested in shock tubes and boundary layers, but if you're interested in IC engines, scramjets, fluid dynamics, plasma-enhanced combustion, there's a lot of possible applications. We didn't talk specifically about plasma species, but we could have. Those ions are also just accessible with the same theory that I've told you about. So, there's a lot of tracers that we could use, toluene, ketones. People always ask, what's a good tracer for high temperature gas? Well, that's a good question. We've used NO, but the complication of NO is that we have to use two lasers. You'd like to use things that are naturally present, not have to add anything. So that's why we worked on CO2 for the infrared. You'd like to use a tracer that would survive at high temperatures, that's such as NO. So the ketones and toluene are only good to about 900 Kelvin. You'd prefer to do something naturally present. There aren't always really good choices. You'd like to work perhaps at higher speed than we did years ago. You'd like to measure multiple parameters at the same time, maybe measure temperature and species at the same time. So anyway, I think there's a lot of possibilities for the future. This is my last slide. What I'm trying to do is leave you with a positive message. There's no doubt that laser diagnostics will continue to be be used more and more. You'll be able to buy commercial packages that work, especially with the mid-infrared tunable diode lasers. That's going to get easier and more cost-effective. I showed you this one idea of CEAS that I think is kind of a breakthrough to make it even more absorption, more sensitive. If you have a lot of money, you can go to one of these high repetition rate systems, but now PLIF systems are expensive. So you've got cheap diode lasers or you've got expensive PLIF systems. You have to kind of pick your poison. Depends on the problem that you have. I told you I got 2 students, actually 3 students down in Houston right now making tests on a 100 megawatt gas turbine power supply. And you know, they're facing the usual problems of optical engineering, but it's working. So there's just no doubt that, and that's portable. So that allows you to work in the laboratory and then go out in the field and make practical measurements. So my point is, I've been working with laser diagnostics since around 1968 or so, a long time. I was lucky because lasers were just invented. You have to always look for the wave, catch the wave. So I caught the laser wave, and so you have to kind of think what the new wave is for you, but there's no doubt that laser diagnostics will be more and more common in combustion. There's just no doubt about it. So whether you're fluid mechanics, combustion, propulsion, whatever you are, you need to learn about thermocouples and you need to learn a little bit about lasers and cameras. I see Professor Law up here checking me out. So he's passionate about combustion and I'm passionate about combustion diagnostics and chemistry. And so I hope you've enjoyed my course. Thank you very much. That's good. All right.